Hey there, science fans. Today we're diving into the fascinating world of electricity with a fundamental law known as Ohm's law. This law, named after the brilliant physicist Georg Simon Ohm, describes the relationship between voltage, current, and resistance in an electrical circuit. Simply put, Ohm's law states that the current flowing through a conductor is directly proportional to the voltage across it and inversely proportional to its resistance. This relationship is neatly summed up in the famous equation V equals sine IR. V represents voltage, which is like the electrical pressure pushing electrons through the circuit. I stands for current, which is the flow of electric charge, like the amount of water flowing through a pipe. And R represents resistance, which is the opposition to the flow of current, similar to how a narrow pipe restricts water flow. Ohm's law is a fundamental principle in electrical engineering and physics. It helps us understand how electrical circuits behave and allows us to design and analyze them effectively. Whether you're dealing with a simple circuit in your home or a complex electrical grid, Ohm's law is always at play. Now that we've got a grasp on the basics of Ohm's law, let's delve deeper into each component of this electrifying equation. Before we explore how resistors work in series and parallel, let's break down the three key players in Ohm's law: voltage, current, and resistance. Imagine an electrical circuit as a system of pipes carrying water. Voltage, measured in volts, is like the water pressure that pushes the water through the pipes. A higher voltage means more electrical push or potential difference, resulting in a stronger flow of current. Current, measured in amperes, represents the flow rate of the water through the pipes. It's the amount of electric charge flowing through a point in the circuit per second. A higher current means more electrons are flowing through the circuit every second. Resistance, measured in ohms, acts like the pipe's width. A narrower pipe offers more resistance to water flow, just like a higher resistance restricts the flow of current. Resistors are special components designed to introduce specific amounts of resistance into a circuit. Understanding the roles of voltage, current, and resistance is crucial for comprehending how electrical circuits function. Now, let's connect these concepts to resistors and see how they behave in different configurations. Resistors, those tiny components with colorful bands, play a crucial role in controlling the flow of current in electrical circuits. When resistors are connected in series, they are placed one after the other, like links in a chain. In a series connection, the current flows through each resistor in sequence, encountering resistance at each point. The total resistance in a series circuit is simply the sum of the individual resistances. Imagine a single-lane road with multiple toll booths. Cars must pass through each toll booth one by one, and the total time it takes to pass through all the booths is the sum of the time spent at each individual booth. The formula for calculating total resistance in a series circuit is R underscore. Total equals R1 plus R2 plus R3 and so on. Connecting resistors in series increases the overall resistance of the circuit. This reduced current flow can be useful for protecting sensitive components or controlling the amount of power delivered to a specific part of the circuit. Section 4. Resistors in parallel, sharing the load. In contrast to a series connection, resistors connected in parallel provide alternative pathways for the current to flow. Imagine a multi-lane highway where cars can choose different routes to reach their destination. In a parallel circuit, the voltage across each resistor is the same, but the current is divided among the different branches. The total resistance is actually less than the resistance of the smallest individual resistor. Now, calculating the total resistance, or R underscore total, in a parallel circuit is a bit more complex than in series, but fear not. The formula is 1 over R underscore total equals 1 over R1 plus 1 over R2 plus 1 over R3, and so on. Connecting resistors in parallel decreases the total resistance of the circuit. This increased current flow can be useful for providing multiple paths for current, preventing a single resistor from overheating or creating circuits with specific resistance values. Section 5. Everyday examples of Ohm's law in action. Ohm's law and the concepts of resistors in series and parallel are not just confined to textbooks and laboratories, they are at work all around us in countless everyday devices. Think about the dimmer switch in your living room. It controls the brightness of the light by changing the resistance in the circuit. Increasing the resistance reduces the current flowing to the bulb, making it dimmer. Another example is your phone charger. It contains resistors that regulate the voltage and current delivered to your phone's battery, ensuring safe and efficient charging. Even our bodies rely on these principles. Our skin, for instance, has a certain resistance. That's why we get an electric shock when we touch a live wire. The current flows through our body because it provides a path of less resistance.